Welcome back, everyone. In this video, we're going to be talking about paired t-tests, or the technique that we use to compare two populations to one another when our observations are tied together in some logical way. Now, in the two-sample test that we talked about in the previous video, our observations in one sample were independent of the observations in the second sample. But in a paired design, the two groups are paired together in some logical way. And what I mean by this is that each observation in group one is logically matched with a corresponding observation in group two. In a paired design, we're only concerned with differences between groups within a pair, and we're not concerned with the differences that occur across pairs. And this is a particularly helpful design when you expect there to be a lot of differences among entities or subjects. In this diagram, then, I'm just graphically depicting the difference between an independent sampling design and a paired sampling design. So in the figure on the right, then, we've got our two samples, purple and orange, but each of the observations in those samples is independent. There's no particular reason why any one observation in the orange sample should be matched up with any other observation in the purple sample. But in the figure on the left, you can clearly see that observations in each of the samples are matched with a corresponding observation in the other sample. So here we have a single location where we have an observation in the orange scenario and the purple scenario right next door. And this sort of paired sampling design, in this case through space, is a really efficient way for controlling for the possibility that there is in fact lots of spatial variation that could contribute to the variability in each of our samples. So let's say, for example, that researchers were interested in comparing fish species diversity in lakes before and after some heavy metal contamination event. Now, lakes themselves might differ a lot in species diversity. And so a paired design allows the researchers to control for all of this variability among lakes by comparing the change in diversity from before the heavy metal contamination event to after using a paired design. So in this case, for each of these three lakes, the researchers measured the number of species of fish in the lake before the contamination event and after the contamination event. And so you can see then that there is a correspondence between this value in the before sample and this value in the after sample because they both come from Canispi Lake. Well, these two come from Lake Opiongo and these two come from Slave Lake. So these observations within each sample aren't independent of one another. They're matched in pairs. And that's what we mean when we talk about a paired design. Now, here's a somewhat humorous example of a paired design from a physician who was interested in testing the hypothesis that cracking your knuckles leads to arthritis. And so the physician cracked the knuckles on his left hand at least twice a day for 50 years, while at the same time leaving the knuckles on his right hand uncracked as controls. And he then tested both of his hands for the presence of arthritis. Now, this is a little bit humorous because although the observations are paired, there is in fact no replication in this experiment because this physician was the only subject in this paper that he published. But incidentally, he didn't find any evidence to support the hypothesis that cracking your knuckles leads to arthritis. Some other examples of paired statistical designs could include comparing a patient's weight before and after hospitalization, testing the effects of sunscreen by applying sunscreen to one arm and a placebo to the other arm of the same individual, or finally, In some clinical trials where treatments can't be applied to the same individuals, what the researchers will do is to intentionally match subjects by age, weight, ethnicity, and other categories with another individual with those matching characteristics, assigning each individual to one of the two treatments. And those two separate individuals are paired because of their similarity in age and demographics and so on. In this particular example of a paired design, Talia Seshli was interested in testing the effect of tree species on hoard rot because Talia was particularly concerned about declines in gray jay populations that might be caused by their caches of food under the barks of trees rotting as a result of warming winter temperatures. And so Talia was interested in testing the effect of the tree species on which the hoard occurred. So she created these artificial caches where she put mealworms in the caches or raisins, which mimic the food of gray jays. And she placed these artificial caches on the barks of different tree species. Now, her primary hypothesis was to test the effect of the different tree species on the perishability of these hordes, but she did this across a latitudinal gradient. And she expected that there would be big differences among her different study locations. And to try and control for this, then, she executed a paired statistical design where within each site, she had one spruce tree paired together with a nearby birch tree. And as a result, this paired design then allowed her to have more statistical power to compare spruce to birch without having to worry about all of the variability that occurs from site to site to site, increasing the variability within her statistical samples. So the reason that we don't have to worry about these differences among groups or among sites or among pairs is because in a paired t-test, what we're actually examining are not the observations themselves, but the differences in the observations within a pair. And so in this case, the null hypothesis that we're actually testing is that the difference between observations within a pair is equal to 0. And so our paired t-test then is essentially a one sample t-test on these differences. So as an example of this, researchers were interested in trying to understand what the effect of a national no smoking day was on worker injuries that would occur at their place of work. And to do this, they compared the number of injuries that occurred before the National No Smoking Day and the number of injuries that occurred on the National No Smoking Day. But because they suspected that there'd be a lot of variability across years, they used a paired design where they compared a day prior to the National No Smoking Day to the number of injuries on the National No Smoking Day within the same year. So here's what the data look like. You can see that for 1987, there were 516 injuries prior to the no smoking day and 540 injuries on the no smoking day. And so each of these observations within each of these samples is logically matched to one another because they both occurred within the same year. And so the group that we're talking about here that we're using for the purpose of pairing is the year, okay? And so the researchers were interested in trying to understand or test whether these no smoking days caused the rate of injuries at workplaces to go up because of the nicotine withdrawal that the workers were experiencing. And so the null hypothesis that we're testing in this case then is that worker-related injuries do not change during these no smoking days. or that the difference between the number of injuries on the no smoking day and the number of injuries before the no smoking day is equal to 0. The alternate hypothesis then is that work-related injuries do change during the no smoking days, in which case the average difference between no smoking days and days prior to the no smoking days would not be equal to 0. And so here's what the data look like again. And all I've done here is to calculate this value, this difference between the no smoking days and the days prior to the no smoking days. And so now we have a set of observations that correspond to these differences between paired observations. And so in our paired t-test, essentially what we're doing then is a one sample t-test on these differences between our two observations within a pair. And so here are our observations, mostly positive, sometimes negative, and we can calculate then what the average difference is, the uncertainty in this difference, and use these to calculate a t-test statistic similar to what we did before. So here is what the data look like graphically. We have injuries before the no smoking day and injuries on the no smoking day. But each of these observations is logically connected to another observation. And so we've just connected those with a straight line. And we can see that most of the lines go up, suggesting that it seems like there might be an increased prevalence of injury on these no smoking days. We can test this statistically by calculating a t-test statistic that looks a lot like our one sample test statistic that we talked about before. In this case, we're simply comparing the mean difference between observations within a pair compared to 0 divided by the standard error of these differences. And here the standard error of the differences then is just calculated as the standard deviation of the differences divided by the square root of the number of differences. So we need to be careful though, because in this case, what we're talking about are the number of differences. And the degrees of freedom then in our paired t-test corresponds to the number of pairs and not the number of observations. So in our example that we talked about with worker injuries on no smoking days compared to before no smoking days, our mean difference between these samples was equal to 25. The standard error of this difference was calculated as 10.22. And so we can calculate a t-test statistic from our paired t-test of 2.45. In this case, we had 10 pairs of observations, so our degrees of freedom are equal to 10 minus 1, or 9. We then want to compare our observed test statistic from our paired t-test to the distribution of test statistics that we expect to get if the null hypothesis is true for 9 degrees of freedom, because the t distribution, if you recall, is defined by the degrees of freedom. And you can see then that getting a test statistic of 2.54 when we have 9 degrees of freedom is really quite unusual. So here we have our test statistic and the area to the right, as well as the corresponding test statistic in the negative direction and the area to the left. The reason we're considering both tails is because our alternate hypothesis didn't have a specified a priori direction, and so we're performing a two-tailed statistical test. Now we can directly calculate these areas using the PT command, as I mentioned before, where this is our test statistic and these are our degrees of freedom. We're interested in the area to the right of our test statistic and not the left. So we can use 1 minus PT, or we can specify instead that we want the upper tail, and so the lower tail is false, meaning the upper tail is true. And because we're dealing with a two-tailed statistical test, and our t-distribution is symmetrical, we can simply take this probability shown in red and multiply it by 2 to get the sum of these two different red probabilities at the upper end and the lower end. We can also perform a paired t-test using the t.test function in R, where we now have two separate columns of observations for the number of injuries on no smoking days and the number of injuries before no smoking days, where we specify that these two columns of observations are logically linked through a paired design. And you can see then that this paired t-test calculates the same test statistic, the same degrees of freedom, and the same p-value as we calculated by hand. As with our other statistical tests, we need to consider the assumptions of a paired t-test. In a paired t-test, we assume that the pairs are chosen at random. The individual observations within a pair are not independent of one another. They're logically paired or tied together, but we assume that pairs themselves are independent of one another. Second, we assume that the differences that we calculate have a normal distribution, which allows us to use this t-distribution to calculate our probability. Now, this doesn't assume that the individual values or observations are normally distributed, only that the differences are normally distributed, because it's these differences that we're using to calculate our t-test statistic. So now we have three different approaches for comparing means to a standard or means to one another using a one-sample t-test, a two-sample independent t-test, and a two-sample paired t-test. And although these are separate recipes, they all have the same basic ingredients arranged in the same basic way. In each case, we calculate a test statistic that is made up of a numerator that measures the magnitude of the effect and a denominator that measures the uncertainty of the effect. So in all cases, a t-test statistic with a larger magnitude means we have a bigger effect size for a given amount of uncertainty, whether that t-test statistic is in the positive direction or the negative direction. In all cases, we're measuring the uncertainty in our estimates by some measure of the sample standard deviation and some measure of the sample size. And in all cases, we need to calculate the degrees of freedom because the t-distribution is defined by its degrees of freedom. So in summary then, when observations within our sample are not independent, but instead are logically paired, then instead of using an independent samples t-test, we use a paired t-test to compare groups. A paired t-test is similar to a one-sample t-test, but now our one sample is made up of these differences between observations within a pair. And this paired design represents a powerful statistical technique to test for differences between our groups while controlling for variation across individuals, sites, years, or whatever we're using in the pairing itself.